Hello and welcome to the fourth video in this tutorial series on how to use the MPT-Calculator. In this video we're going to show you how to use constructive solid geometry to create the earring that you see in front of you. We're going to do this using ngsolves.geo file format. Additionally, we're going to show you how to set some material properties for the object so that it's ready to run using the MPT-Calculator. So at this point you should have ngsolve, Python 3, and the MPT-Calculator all downloaded and installed. If you haven't got that yet, have a look at video 1 on how to install these. Without anything else, I hope you enjoy the rest of the video. Thank you. Okay, so in order to create the earring that we've just shown you, we've defined a .geo file. There's several different parts to this .geo file, and we're about to walk through them and explain what each part means. But the four key bits are the outer domain, the primitives and different parts of the object, how we've combined these parts, and then defined top-level objects. So we're going to go through these one by one. So firstly, defining the outer domain. So for each simulation we run, we have to define an outer box, at which point we say there's no more electromagnetic activity outside here. So what we've chosen is a box or cube that is 1000 by 1000 units. So if we combine this with an alpha of 0.001 meters, that would give us a box of 1 meter by 1 meter by 1 meter. And since we're considering an earring which is about 10 millimeters long, our outer domain is about 100 times the size of the object of interest. This is key because we're going to say that the perturbation caused by the earring at the outer domain is negligible and just set it equal to 0. In the next part of the geofile, we've defined the earring itself. We've done this using the primitives that are offered by ngsolve or netgen, and we're going to provide a link to the documentation for this, as it's far more thorough than I can be. However, I will tell you how we've defined the earring instead, and we've done that in 3 parts. So firstly, we've defined the ball on the end, we've defined the bar in the middle, and then finally we've defined the flat end. So we've got a ball which is 1 millimeter in radius, we've got a 6 millimeter long bar which is half a mil in radius, and then for the end we've got a cylinder which is 0.5 millimeters long and 1.2 millimeters in radius, which we then combine together in the next part, defining the earring as a whole using the Eulerian operators. So for the earring, we're interested in the ball or the bar or the end. To define the non-conducting region, we simply define this as the rest of the domain, and then use the and not operator for the earring. So we're interested in the domain and not the earring. Finally, we've got to define these as top-level objects in order to be able to mesh them. So we do this by saying top-level object, or TLO, rest. So we do that for the rest, and then we also do that for the earrings. Sorry, I should actually say earring. In NetGen, we can also visualize the objects. So the rest of this line, up to the semicolon, is about how we're going to view this in NetGen, and similarly for the earring. The final addition that we've made is this little tag here. So when we say hashtag air, this means that the rest of the object, it will have the properties that air does for our simulation. Similarly, we've given the tag hashtag earring to define the earring's properties for the simulation. For more information on how to create your own geofile and how to tag specific regions of a mesh with material properties, please see section 5 of the MPT-Calculator.pdf. With this, we're ready to visualize our object. So to do that, we're going to open up NetGen. We do this by opening the terminal window, typing the command netgen, and clicking enter. After opening NetGen and trying this for the first time, I noticed there was a slight mistake in the earring.geo file. This only affects the visualization of the geometries and won't affect the mesh that's outputted at the end. But I've just changed 2 lines here. So I've changed the 1 to a 10, and then this 0 to a -1. As I say, this will only affect the visualization of the geometry and not the end result though. So once we've opened NetGen, we can load the geometry file, We do that by saying File, Load Geometry, and then when the Finder window is opened, we click on we navigate to the geo files, which is where the earring.geo is saved, and then click earring.geo, open. So once we do this, we're greeted with a big blue box. So this is our outer domain, which we've defined here as transparent and given it the color 001, which is blue. So we can zoom in, and then we should find at the center of this box, we've got our earring. So having a look at this, we can have a look around and decide whether we're happy with the geometry. If we decide that we're unhappy with the geometry, however, we can go back to the .geo file and edit it slightly. So looking at this, I think I'd like to make the ball on the end slightly bigger. So what I'm going to do is go to where the ball is defined and change this to have a radius of 1.5 millimeters as opposed to a radius of 1. So saving that, we go back into NetGen and say File, Load Geometry, and it's the same process. We have to reload the .geo file. So opening that up, we're greeted again with the big box, and zooming in, we find that the ball on the end is quite a bit bigger. So I think that this looks slightly too large now. So what I think we're going to do is change it again to be 1.25 instead. So same thing again. We load the geometry and then reload earring.geo and zoom again to find the geometry. So looking at this, I think that looks a bit better. One more thing we might want to do though, however, is take part of the object away. So instead of having the earring to be made up of all of these three parts, we could take one part away. So say we didn't want the bar in the middle anymore. I don't know why you'd want that as an earring, maybe it's magnetic or something. So if we save that and then reload the geometry, we'll find something slightly different this time. So zooming in, we find out that the bar in the middle has disappeared. As I'm sure you'll agree though, it's probably best if we keep the bar there though. So we're just going to go ahead and put the bar back, as we said, or bar. And finally we're going to revert the sphere back to its original shape, which was of radius 1. So doing that and then reloading once more. We should end up with what we had originally, which is our original earring. Up till now, we've only been talking about the geometry of the object. So next we're going to talk about the mesh. So we can compute a mesh for the object by simply clicking Generate Mesh. So doing this, NetGen will produce a mesh of our domain and our earring inside the domain. However, when producing this, we haven't given NetGen any information about how we'd like the mesh to be computed. So all it's done is used its default settings. So to get to them, we can click on Mesh and then Meshing Options to see what is actually used. And we find out that we've produced a moderate mesh, and we've got a couple of different options in here. But first and foremost, I just worry about this bit here. So the mesh has been computed, so we have a mesh for our domain and our object. So I'm just going to zoom in so we can see the mesh for the object specifically. And at first look, it looks to be a pretty good mesh. So just using the default settings, we've produced what would be a pretty reasonable mesh. We do, however, note that there are some sort of sharp edges along the sides of the curved edges. So we might have to do a little bit of refinement around these so that our discretization of the object is slightly better. So we can do this by changing the .geo file in order to provide some information about meshing. So we're interested specifically on adding constraint to the size of the elements in the earring. So we're not worried about the outer domain, since it's got no curved edges. The discretization for this is pretty good. So we can add a constraint here by saying dash max h equal, and then we can decide how big we'd like the elements to be. So I'm going to start off by saying 0.5 units long. So this is an educated guess, and we're sort of going for a bit of a Goldilocks zone, so that we've got a good discretization by having small enough elements, but not so many elements that we're going to end up making our simulations run slower. So with this, we can save our .geo file, and then we need to reload it. So we'll say reload geometry, and then load earring.geo, and then say generate mesh. So once again, this is going to generate a mesh, and hopefully we should end up with a slightly better discretization for our earring. So NetGen has finished creating our mesh, so we're just going to zoom in and have a quick look at our object. So looking at it again, it doesn't seem to have changed much. So this probably suggests that the elements in the earring already were smaller than 0.5, which is okay. It just means that we might need to make the max h a little bit smaller. But it's better to start off too big with the max h than too small, as it'll take longer to generate a mesh, to only find that you've got too many elements to deal with. So I'm just going to center this again, and then change this to be 0.25 instead. And then doing the same process, we say load geometry, we load the earring.geo file, and then say generate mesh. So NetGen has finished meshing our domain, so we're just going to zoom in again and then have a look at our object. Okay, so looking at this now, we can see that we've got quite a few more elements. We can also see that, I don't think you can see that, I'm just going to move him over here instead. So you can see that we've now got 28,000 elements in our mesh. Previously we only had about 22,000, and the second time we're meshing we had about 24,000. So we've got a couple more elements to play with now. And as you can see, we've got a better discretization. So with this discretization, I think we're about ready to run a simulation. To do that, we have two options. Firstly, we can get main.py to point to this geometry file and set the mesh sizing to be equivalent to the mesh that we've just generated. So in our case, we've generated a moderate mesh, which correlates to the mesh sizing parameter being equal to 3. Either that, or we can save the mesh that we have just computed and then reload it in the settings.py file by setting old mesh to be true. So we're going to do that for the minute. So we're going to save this by saying file and then save mesh. And then I'm going to expand this into a Finder window. And then we need to save this in vol files. So we'll go up one file and then click on vol files. So already it's got the right name. This should happen automatically, but just check that just in case. And click save. So with that, we've saved our mesh, and it should be in here. So now we can go ahead and load this in our simulation. So I'm going to close NetGen and close the .geo file, open main.py and open settings.py. Okay, so similarly as in the last video, we're going to run a simulation for the object that we're interested in. So we're first going to go on main.py and make sure we're pointing at the right geo file. So if you've worked along with the last video, you should have yours currently pointing at sphere.geo, but instead we want to change ours to point at earring.geo. The other thing to note is that instead of having an alpha of 0.01 meters, which would make all of the units in our .geo file be in centimetres, we want to instead have this in millimetres, since that's how we've defined our object. Next, we want to have a look at our mesh sizing. So this isn't going to be used currently because we're going to run with the mesh that we've just created. But to create the same mesh, we would have to put mesh size equal to 3, as this is equivalent to moderate for NetGen. But we'll leave that at 2 for the minute because it doesn't affect the simulation. As far as the order of the elements go, we're going to start off with an order of 3. So we're going to run the same sweep as last time using proper orthogonal decomposition and also multiprocessing. So we'll save this. And then in the settings file, we're going to use 2 cores. It's not a big problem. We're going to use the settings that we've used for the last one. And then finally, we need to change this to say old mesh equals true. So at this point, we're ready to run our simulation. So we do this by making sure that we're in the correct folder, which is MPT-Calculator-master, and then running the command python 3 main.py. So then clicking enter, this will load the old mesh and run the simulation for our earring. Okay, so the frequency sweep is finished running now. For me, that took about half an hour, and at peak usage, I was using about 3.2 gig of RAM. I've gone ahead and closed the graphs, and then I've opened up the results folder into the frequency sweep that's just been produced. So I'm going to go ahead and open the imaginary part of the tensor graphs, so we can have a quick discussion on the results that we can see in here. Okay, so the first thing that we notice is that in comparison to the sphere graph, the peak height has been, or the whole graph pretty much has been shifted to the right, and we notice that the end's been cut off. So this is due to us considering a much smaller object than we did previously. If you remember, we had a sphere of radius 1 centimetre, whereas this earring we're considering is about 8 millimetres long. We also notice that the height of the peak is much smaller. We're talking with something 10 to the minus 9 in comparison to something that was 10 to the minus 6. So in order to counteract this, what I suggest we do is that we run another simulation, but this time we're going to run it at a slightly higher frequency. So we're going to run it between 10 to the 2 and 10 to the 10. That way we should be able to get all of the information that we're interested in the frequency sweep. So all I'm going to do, I'm just going to close the graph, and I'm going to go back into main.py and then change the start and end of the frequency sweep. So we'll change that to 10 to the 2 and change this to 10 to the 10. So hopefully at this point we should end up with something that has a bit more useful information in it. So I'm going to head and run this using the same command as we did previously, and then I'll catch up with you once it's finished running. Okay, so that's finished running now. I decided to turn my screen grabber off this time, so it ran a little bit quicker for me. It took about 15 minutes this time, and again used about 3.2 gig of RAM at peak usage. So I've gone ahead and I've closed the original graphs that were outputted, and instead opened up the imaginary parts of the tensor for each of the frequency sweeps we've just run. So we've got the original one on the left, and then the one that we've just run on the right. And as you can see, there's a slight shift to the left for this graph here on the right, and that's due to the frequencies that we're interested in this time. So as you see on the x-axis, the frequency axis, we're outputting some values for different frequencies this time. One other thing to note is there's a slight bump here. You might be able to see it a bit clearer on this one. So this suggests that we may need to do a bit of P refinement, so increase the order of the elements. So I'm not going to do that in this video though, due to the length of the video, but if the user would like to do that, then please rerun the same simulation, but this time with the order equal to 4. So with this, we're going to draw the video to a close. In the next video, we're going to discuss the outputs for the MPT calculator, and how to obtain additional outputs such as a VTK file to help you visualize the eddy currents in your object. I hope you've enjoyed listening to this video, and I hope to see you in the next one. Thanks for listening.